Hi everyone, see you again on CHM421, which is analytical chemistry. We will continue our learning on topic 4, titrimetric analysis, specifically on acid-base titration. Titration using acid in base solution. So first of all, we should know a little bit the theory on acid in base. So we can explain the acid in base using several theory. Either we use the Arrhenius theory, Bronsted-Lowry theory, or Lewis theory. So what is Arrhenius theory? Talking about acid and base. For the Arrhenius theory, he said for any acid, it should be the substance that contain hydrogen atom, and it can produce hydrogen ion in aqueous solution. So the example of acid, hydrochloric acid, nitric acid, sulfuric acid. However, for base, any substance that contain hydroxyl group introduce hydroxyl ion for each minus in aqueous solution. So a common example of base, sodium hydroxide, calcium hydroxide. So for the Bronsted-Lowry theory, acid is a proton donor. Okay, remember the Arrhenius said any substance containing hydrogen can produce hydrogen ion in the solution. We call it acid. For the Bronsted-Lowry, it said acid is a proton donor. So the after donate the proton, so the compound we call it conjugate base. Conjugate base is a species formed when we remove the proton from the acid. Meanwhile, for base is a proton acceptor. The species formed after we accept the proton or either the proton to the base is a conjugate acid. So in the Bronsted-Lowry, they have acid conjugate base, base conjugate acid, acid proton donor, base proton acceptor. Okay, example of Bronsted-Lowry acid and water solvent. The water acts as the Bronsted-Lowry base. Okay, so acid, for example, we have HA, and water is the Bronsted-Lowry base. So HA, we call it Bronsted-Lowry acid. Okay. Remember, acid, according to Bronsted-Lowry, is a proton donor. So the proton will be removed. So when the proton is removed from the acid, it becomes conjugate base. Conjugate base is a species after we remove the hydrogen. This is why it left over A minus, because HA removed is H plus. So the conjugate base in ion A minus. So the base will receive the proton. Base will accept H plus to form conjugate acid. Conjugate acid is a species when the proton is added. All right. So I hope you can understand the difference between acid and conjugate base, base and conjugate acid. Remember, in the Bronsted-Lowry is about proton donor or a proton receptor. So the Lewis theory. Lewis theory is highlight about the role of electron pair. Okay, Arrhenius produce proton uh, uh, or Arrhenius said produce a proton or produce hydroxide. Bronsted said a proton donor or proton acceptor. However, in the Lewis, acid is electron acceptor. Electron acceptor for acid and base is electron pair donor. So you have to be clear the difference between these three theories. Proton, proton, electron. Proton produce proton, proton donor, electron acceptor. Produce hydroxyl, proton acceptor, electron donor. So you have to know the difference between these three theories. All right. So Lewis acid is electron donor because Bronsted said is a proton. Uh, sorry, Lewis Bronsted-Lowry said is a proton donor. So meaning that Lewis acid it should be electron pair receptor. Okay, so this Lewis acid will accept the electron pair from the Lewis base. The Lewis base is the electron donor. Okay, Lewis acid is an electron acceptor. Lewis base electron pair donor. Okay, so this is the example. The Lewis base, the electron donor. Okay, so this is a lone pair of electron. The lone pair of electron will be donating into Lewis acid because Lewis acid is electron pair acceptor. Lewis base is electron pair donor. All right. So to form the Lewis acid base complex. All right. Now we discuss a little bit on the strength of acid and base. The strength of acid and base or base is depending on the degree of dissociation of the acid or the base in water. Remember, the strength is depending on the degree of dissociation. So strong acid, it should be dissociated completely. Dissociate to produce a high concentration of hydrogen ion. So this is the example of strong acid. Meanwhile, weak acid is dissociate partially. It produces a low concentration of proton ion. So this is an example of weak acid, acetic acid or phosphoric acid. This diagram is show the schematic diagram about complete dissociation of strong acid. So the strong acid, for example, HA before dissociation, After dissolved in water, the HA will be dissociate completely. So no more HA. So HA dissociate into the A minus and form hydroxyl ion H3 or minus. So this is for the strong acid. So because if complete dissociate in the water, so the arrow is a single direction. All right. So the acid will produce H plus and then to react with water to form hydroxyl ion. And then the A will be this A minus. All right. So for incomplete dissociation of weak acid, for example, we have HA because of weak acid, so it dissociate incomplete. So we in the product we still have a certain amount of HA and low concentration of hydroxyl ion and also an ion. So as you can see, the arrow is a reverse reaction because it's incomplete dissociation. So the concentration of the hydroxyl ion low is compared to the strong acid. The concentration of hydroxyl ion is high. All right. Uh, As we mentioned just now, the strength of acid or base is depending on the degree of dissociation. So the strength of acid is depending on the ability to donate the proton. Because general formula for acid is Ha. So this acid, when dissolved in water, it can dissociate the proton can be produced react with the water H3O plus and A minus. So this is the hydroxyl ion. So the strength of the acid is depending on the ability to donate the proton, the ability to donate this proton. So the stronger the acid, greater the tendency to donate the proton to the base. The stronger the acid, meaning that the weaker the conjugate base. This one is Bronsted-Lowry theory. The weaker the acid, stronger the conjugate base. Okay, this one is very straightforward. So we have a few examples of acid with conjugate base. When the proton donate, so it form a conjugate base. As I mentioned, conjugate base is a species after we remove the proton. Okay, so as you can see, all the proton removed, so it becomes Cl4 minus. So no need to remember this one. It's just to make you some idea about it. We have a strong acid. We can have a weak acid. Is the acid strength can be increasing. Base strength can be increases. You also should understand what is the acid, what is the conjugate base. Okay, all right. So just now we discussed about the dissociation of strong acid and weak acid. So now we discuss a little bit on strong base and weak base. Strong base dissociate completely to produce hydroxyl ion. So it produces higher concentration of hydroxyl ion OH minus. So this is the example of strong base. Normally it's a hydroxide of group 1 or group 2 metal. So for the weak base, similar to the weak acid, it dissociates partially. It produces low concentration of OH minus. So this is a few example of weak base. Ammonia, uh, ethylene, ammonia. All right. So strong base dissociate, as I mentioned just now, a strong base dissociate completely to form hydroxide ion in aqueous solution. Dissociate completely meaning the arrow is a single arrow. So the OH minus will be dissociated to form OH minus. So it lift over the this one we call it conjugate acid, a species formed uh, after remove a proton. Okay, so weak base is do not dissociate completely to form hydroxide ion in aqueous solution. So the arrow should be a reverse reaction. So the concentration of OH minus for weak base normally is lower is compared to the concentration of OH minus for the strong base. Okay, so if you still remember in the titration, we use indicator. Indicator we it on with the analyte uh, in the conical flask. So now we learn a little bit on the indicator. So the acid phase indicator function by changing the color just after the equivalent point of the titration. This color change we call it N we call it N point. Again, the acid base indicator function by changing the color just after the equivalent point of the titration. This color change is called end point. The end point is most often detected visually because we can see the color changes. Most of the acid base indicator are organic dye molecule. It can be acid or it can be base. Okay, indicator can be monoprotic or it can be diprotic. As you can see, monoprotic acid is only one proton. Diprotic acid indicator is containing of two protons. The acid form of indicator is usually colored. When it loses the proton, resulting in ion or this form of the indicator, it exhibiting another color. So, uh, When the indicator loss of the uh, proton, the color will change. Okay, from uh, one color one color to another color. Uh, Diprotic acid indicator H2IN, it will ionization two step into two step. First, you can observe the diproton. The diproton H2 will be dissociate or ionized into H. So it changed from one color to another color, and then it can be further ionized. It can be further ionized to form H plus. So it can form another color. So you just remember indicator, it can be monoprotic or diprotic. So normally indicator is invoke the color changes from one color to another color when the indicator loss of proton. So for the diprotic, it will loss of proton in two steps. Step number one proton removed, and step number two, the second proton removed. So for selecting and using indicator, uh, to choose indicator, the choose indicator should undergo the distant color change because we want to detect the end point. So the indicator have to change the distant color at the equivalent point through endpoint. So choose indicator whose a middle half of the pH transition range. Because in the pH transition range, the indicator should show the greatest color change. For the indicator color change, it should be detectable by using naked eye. So this table gives you various option of indicator uh, for the transition of color can be happen at this range of pH. So we have to be very careful to selecting the indicator, and the color change from acid to base, base to acid uh, is indicated in the table. No need to remember this, but as long as you remember, you know, we have various option of indicator. The color of the indicator will be changing in the particular range of pH range. Okay, so the color it should be changed from one color to another color. Uh, the color changing it should be very clear or it should be a very instant. All right. So choose when we do the titration, we should choose the indicator where the change color at the step section of the curve. Okay. So the color changing happen in step, the step section of the curve. So we know the color changing, which is the color changing after the equivalent point. So the equivalent point it should be on the step section. Okay. in order to know whether the color is already changed or not. So when the color change after reach the equivalent point, the final color we call it end point. So end point is a point at which the reaction observed to be completed. This is why we call it end point. The end point in titrimetric analysis is the signal that tell us the person do the analysis to stop adding the uh, titrant or adding the reagent from the burette and make the final reading in the burette. So endpoint is observed with help of suitable indicator because indicator will change the color from color A to color B in particular pH range. So before we start the titration, the analyte uh, with titrant have some equivalent point. When we put the indicator, it has a color. The first color, color 1. So after the reaction reach the equivalent, the indicator will be reacting and produce another color. This last step is does not require all indicator to be converted. It's the best if only small percent, only a small percent. So meaning that it's not over titration. So it's just one drop or two drops of the titrants can change the color significantly. So no need to convert all the indicator. So we need for the best of is the best if the small percent of need to be reacted to make the change visible to reach the end point. Okay, equivalent point. Equivalent point is the point at which equivalent or stoichiometric amount of titrant is added to the analyte. Two solutions exactly neutralize each other. So, for example, we have uh, acid-base titration. So, acid-base chemical, it should be neutralize each other. So that's the equivalent point of the neutralization. We call it equivalent point, where the equal amount in mole of in equivalent amount of proton and hydroxyl ions. So the volume of titrant are required to just completely react with the analyte is the titrant. Okay, so I think that's all for this video because I don't want to give you a lot of information because this subtopic acid-base titration is quite long. So we try to cut off the video into a small section. So on the next video, we will learn in detail a different type of acid-base titration. Okay, so that's all for this video. See you again on the next video on the types of acid-base titration. Okay, thank you. Bye-bye.